Hi, welcome to this lecture on built-in types of data. Here's the outline for this lecture. We'll first talk about what types are, then I'll give you some definitions of some very important concepts, and then we will move on to talking about four built-in types in Python, namely strings, integers, floating point numbers, and booleans. And then we will discuss functions, how you invoke them and so on. And we'll also talk about the concept of an application programming interface, or API for short. And then we will discuss how you convert types, meaning how do you go from one type to another. And then finally, we will discuss how you use the Python interpreter as a very simple calculator in an interactive mode. All right. So what is a type? Well, a data type is a set or collection of values along with a set of operations that are defined on those values. Okay, so each type allows for a range of values, and you can perform a certain set of operations on those values. So that's what a type is. A type always specifies a set of values and the allowed operations on those values. Python supports several built-in types, and the four fundamental built-in types are int for integers, float for floating point numbers or real numbers, stir for sequences of characters or strings, and bool for true-false values. Okay, so these are the four fundamental or basic built-in types in Python. And in addition, Python also supports other built-in types. All right, so this lecture is going to be on the four fundamental built-in types, namely int, float, strings, and Boolean. And we will save the other built-in types for a future lecture. Now, in addition, Python also allows you to compose or define your own data types, meaning Python supports object-oriented programming. So that's a topic for a future lecture as well. Right? So in this lecture, we are going to focus on the four basic built-in types, namely int, float, stir, and bool. Let's first start with a few definitions. The first definition is that of a literal. A literal in Python is simply Python code representation of a data type value. All right. So for example, if you want to talk about numbers such as 99 and 1234, you would simply write them as such in your Python programs. And that's why these guys are called integer literals, because they literally show up as is in the Python code. Okay, so this is how you would write 1234, and this is how you would write 99. So these are literal ints in Python. What about real numbers? So say you want to talk about an approximation of pi, or Euler's constant. So how would you write it in Python? Well, you would write it exactly as is. So these are floating point literals, all right, or float literals for short. And then what about Boolean literals? Well, if you want to talk about true, you write it as true with a capital T. And if you want to talk about false, you write false with a capital F. So these are the two Boolean literals. Okay. And then finally, if you want to talk about a string in Python, what you do is you simply embed the characters that make up the string inside of matched single quotes. So here we are talking about the string literal hello world. Okay, so that's what a literal is. A literal is simply a Python code representation for a data type value. So these guys are integer literals, these guys are floating point literals, these true and false are Boolean literals, and this guy here is a string literal. Okay, next is the notion of an operator. So what is an operator? Well, an operator is Python code representation of a data type operation. All right. So for example, the characters plus and star denote the addition and the multiplication operations on integers and floating point numbers. Okay, so those are arithmetic operators. And then these guys, and, or, and not, they represent Boolean operations. All right. So these are Boolean operators in Python. So an operator is nothing but a representation in code of a data type operation. The next idea is that of an identifier. An identifier is simply Python code representation for a name. All right. And an identifier has a very specific syntax. It is a sequence of letters, digits, and underscores. So an identifier can contain letters, digits, and underscores, but it cannot start with a digit. All right. So the only characters that are allowed as part of an identifier are letters, digits, and underscores, with the additional rule that the identifier cannot start with a digit. Okay, so let me give you some examples. So ABC is a valid identifier. Why? Because it meets this requirement. It simply consists of letters. AB underscore is also a valid identifier because again it meets the definition. ABC123 is also valid, and so is A underscore B. So all these guys satisfy the definition. Okay. But what about these guys here? AB star is not a valid identifier because star is not an allowed character. Okay, one ABC is not an identifier because it starts with a digit, and that's not allowed. And then finally, A plus B is not a valid identifier because plus is not an allowed character. Okay, so that's the notion of an identifier. It's simply a sequence of letters, digits, and underscores, the first of which is not a digit. Now, there are certain identifiers in Python which are called keywords. So for example, and, import, in, def, and so on, these are all keywords, and they're reserved in Python. Okay, so you cannot use them, you're not allowed to use them as identifiers. And then there are other identifiers such as int, sum, min, max, and so on, which have a special meaning or status in Python. So it's best to not use them either as identifiers. Okay, so there are some keywords which you cannot use as identifiers, and then there are these special entities in Python which you don't want to use as identifiers. Okay, just so you avoid any confusion. All right. The next idea is that of a variable, which is a fairly important concept. So what is a variable in a programming language? Well, a variable is simply a name that is bound or associated with a value, with a data type value. Okay, so for example, you might have a variable called total that represents the running total of a sequence of numbers such as 1 plus 2 plus 3 and so on. Okay, so you might store this result, this running total of a sequence of numbers, in a variable called total. All right, so total is assigned or is associated with the value that is given by this running sum. Okay, now a constant variable is a special kind of variable whose associated value does not change over the course of the execution of the program. All right. In other words, a constant variable takes on a value and that value remains fixed for that variable. Okay, it does not change over the course of the program. So for example, you might have a variable called the speed of light that represents the known speed of light. Now the speed of light is a constant, so we want to represent it using a constant variable. All right, now by convention, constant variables are named all uppercase. That's just a convention. All right, just so that you know when you read someone's code and when you see a variable whose name is all uppercase, you know that it represents a constant of some sort. All right. Okay. Now the next concept is that of an expression, which is an extremely important concept. And an expression is nothing but a combination of literals, variables, and allowed operators. All right, which then evaluates to produce a value. Okay, so every expression has a value, meaning it has a type associated with it. Now the simplest kind of expression is a literal and a variable. All right, so if you have a literal such as 42, then it is an expression by this definition. Similarly, if you have a variable, let's say x, of type integer, then that is also an expression by this definition. Now, this definition also says that you can combine these two guys using allowed operations to build a more complex expression. So this is an integer, this we said is an integer, so you can combine them, for example, using an arithmetic operator such as plus. Okay, and that gives you an expression x plus 42, which by this definition has a value and it also has a type. So in this case, the type is going to be int. Okay, and then if you have another integer, let's say y, you can combine that with this expression using, let's say, the arithmetic operator star to give it to produce an even more complex expression, which is that whole thing. And by that definition, that expression also has a value associated and it has a type associated with, which is an integer. Okay, so you guys, so you get the idea. An expression is simply something that you build from these basic expressions such as literals and variables using allowed operations. And every expression, there is no exception to this rule, every expression has a value associated with it and hence a type associated with it. All right. So here is another example of this idea. So let's say you have a variable x that is of type integer. All right. So what we have done is here we have combined that variable expression along with this literal, this int literal expression using the arithmetic operator subtraction to produce this expression x minus 3, whose type is integer and it has some value. And then we combine that expression. So we combine now this expression with 4, which is an integer literal and hence an expression, to produce an overall expression which has some value and whose type is an integer. All right. Okay. Now, with expressions, Python has a natural and well-defined set of precedence rules, all right, which fully specify the order in which the operators are applied in evaluating that expression. So for arithmetic operations, we all know that multiplication and division need to be performed before addition and subtraction, and that's exactly what Python will do. So multiplication and division will be performed before addition and subtraction. So if you have something like 2 plus 3 times 4, then it's the multiplication that's going to be carried out first because of the precedence rules. And then the addition will be carried out. So here the result is going to be 14. All right. Now, when arithmetic operations have the same precedence, then they are left associative, meaning things get evaluated left to right, with the exception of the exponentiation operator, which is given by 2 star signs, which is right associative, which is evaluated right to left. So let me give you an example of that. So let's say you have something like 2 plus 4 minus, let's say, 3 star 2. Okay, so here notice this is an expression where you have two operators, two arithmetic operators with the same precedence, plus and minus. So things are going to be evaluated left to right if you just had those. But then you also have this exponentiation operator here, which is right associative. So this thing is carried out first, which gives you a 9 because it's 3 square, and then you evaluate this expression 2 plus 4 minus 9 in a left to right fashion. All right, because plus and minus have the same precedence. Okay, and then finally you can use parentheses to override precedence rules. So for example, going back to this example here, 2 plus 3 times 4, let's say you want the addition to happen before the multiplication. How would you achieve that? Well, simply put parentheses around 2 plus 3. All right, so in this case, the addition is going to take place first and then the multiplication, so you end up getting the result 20. All right. Okay, now we've talked about what a variable is and what an expression is and so on. Now let's talk about how you define a variable, right? And that brings us to the very first assignment statement, which very first statement form, which is the assignment statement. All right, and the syntax for an assignment statement is extremely straightforward. And the assignment statement is what you use to assign a value to a variable. So the syntax is, you put the variable name, and then you put the equal sign, and then you put an expression whose value will become the value of the variable. Okay, so the syntax is variable name equals some expression. Let's take an example. So we can, if we want to define a variable called a with the value 1234, this is the syntax that we would use. So the variable name is a, and then the expression is simply an int literal, 1234. So once this statement is executed, what happens is it defines a variable called a, okay, whose value is said to be the integer 1234. All right, so that's the syntax for defining a variable. Now in Python, to represent the absence of a value, we use the keyword none, right, with a capital N. So if you say some variable name equals none, then that variable really does not have a value. All right, so none is what we use to denote the absence of a value. And we'll see the use of this later on in the course. Now, all data values in Python are represented by objects, and each object is characterized by its identity, meaning its memory address. And then it's also characterized by its type and value. Right? So for example, when you define something like a equals 1234, a has some location in memory, all right? And then a has a type associated with it, which is simply the type of this expression here, that's integer, right? And then a also has a value, which in this case is 1234. All right, so in Python, everything is an object, and each object has three things that characterize that object. Its memory location, its type, and its value. So, for example, the figure here on the left shows how the variable a, which is defined here, might be represented in memory. Right? So a, the variable name, simply stores a memory address. For example, it might be something like 460. That's just a memory location. Right? And if you go to that particular memory location, to location 460, what you find is the identity of that variable a. Right? So that's where you find the variable's value, which is 1234 in this case, and also its type information, and in this case its type is an integer. Okay, so again, the way things are organized in Python is that a variable is simply a memory address, and at that memory address you find information about the value of that variable, and you also find information about the type. Okay, now this figure here on the right just shows how you think about a variable conceptually. So you can think of a as simply pointing to the value 1234. Right? So this is how you would think about a variable conceptually, and here is how it's represented in memory. Okay. All right. Next, consider the piece of code that is shown here that is responsible for exchanging the values in the variables a and b. So initially A is 1234 and B is set to 99, but we want to exchange them. We want to write some code such that at the end of that code, A takes on the value 99 and B takes on the value 1234. Okay, so how do we achieve that? Well, the way we achieve that is using the standard idiom that's shown here. All right, so you first say a temporary variable such as t equals whatever the value of A is. So t is simply now 1234. All right, and then you say the new value for A is whatever is in B. Well, what is in B? It's 99, so A now becomes 99. All right, so that's t, that's A. And then finally we say the new value for B is simply whatever is in temp, right, which was 1234. But now notice that once these three lines are executed, you have A equals 99 and B equals 1234. So the values of A and B have been exchanged. Okay, so this is basically the idiom that you would use to swap or exchange the values of two variables. And this is indicated by the object level trace that is shown in this figure here. So B pointing to 99, A is pointing to 1234, and then when we say t equals A, t is basically pointing to whatever A was pointing to. So t is 1234. And then we say A equals B in the second line. What does that do? Well, in that case, A points to whatever B was pointing to. So A is now pointing to 99. And the last step is saying B equals T. What does that do? Well, B then points to whatever T was pointing to, which is 1234. But now notice that B points to 1234 and A points to 99, right? So the values of A and B have been exchanged, all right? They were 1234 and 99 before, now they are 99 and 1234. Okay, the next thing that we're going to do is talk about the very first of the four fundamental built-in types in Python. Remember, there are four built-in types in Python: strings, integers, floats, and booleans. And we're going to first discuss the string data type. Right? So the string data type, denoted by the keyword str, represents strings in Python. What is a string? A string is nothing but a sequence of characters which you typically use in text processing. All right? Now, a string literal is specified by enclosing a sequence of characters in matched single quotes. So that's how you construct a literal string. Right? So for example, AB enclosed in matched single quotes represents a string literal. So that's now a string literal. Right? Okay, similarly, what we saw in the previous section, hello world, is also a string literal, right? Since it is embedded in matched single quotes. Now, you can specify the special tab, new line, backslash, and single quote characters using what are called escape sequences. So what this means is, inside of your string literal, so let's say you want to write the string Python is great. You want to write this as a string, all right? Now there is a problem here because there is an apostrophe, a single quote here that we want as part of the string. But Python is going to look at this part as one string literal, and then it's going to complain about the rest. So it's not going to know that you want the whole thing, Python is great, as a single string literal. Okay, so what you need to do is escape this single quote that you want as part of the string using a backslash character. Okay, so if you want a single quote inside of a string, you need to escape it. Similarly, if you want a backslash inside of a string, you need to escape that. and the way you express new lines and tabs is using these escape characters, \t and \n. Okay, so these are what are called escape sequences. Now, you can take two strings and concatenate them together, meaning jam them together using the plus operator. So you can use the plus operator to add two strings, so to speak. And the way addition works on strings is by simply concatenating their values. All right. For example, if you take the string 1, 2, 3 and add it to the string 4, 5, 6, then you get a new string whose value is the string 1, 2, 3, 4, 5, 6. Okay. So notice this is not arithmetic addition. This is basically string concatenation. The two strings are just jammed together. All right. Now it turns out that in Python you can also multiply a string object s by some number n to obtain a new string object whose value is the string s repeated n times. Okay, so you just make n copies of that string. So for example, you can do something like 3 times the string literal ab. Or you can even say the string literal AB times 3, and both of these expressions have the same effect in that they produce a new string whose value is the string AB repeated 3 times, AB, AB, AB. As another example, let's say we say Bob times 2. Well, this is going to give us the string Bob repeated twice. Okay. So here's a summary of the string data type then. Now remember that the data type definition, it's basically a range of values with allowed operations on those values. So what are the values for a string data type? Well, it's simply sequences of characters. All right, so any sequence of characters is a valid string. And then typical string literals are literals such as these. And notice here, if you want a single quote inside of your string, you need to escape it. So that's what we have done here. What are the operations that are allowed on a string? Well, it's the concatenation operator and the multiplication operation, right? And concatenation is denoted by plus, and this multiplication is denoted by star. So now let's look at a concrete program that makes use of the string data type, right? So this program is called ruler.py. And it basically shows you how you work with strings, right? So let's go through the program. So what we do here is we first import the Stdio module. We do that because we need to use the print functionality from the module. And then we have an empty line, and then we declare a variable called ruler1, whose value is set to the string literal 1, right? So 1 is embedded in single quotes, so that's a string literal. That value is assigned to ruler1. So ruler1 is just the string which is given by that string literal. And then what we do is we define another variable called ruler2, whose value is set to be ruler1, which is this guy, plus a string literal, plus the value of ruler1 again. So once this is done, ruler2 is going to be what? 1 followed by a space, followed by 2 space, and then 1. Okay, so that's what ruler2 is going to be. And then we define, so that's ruler2. And then we define ruler3 to be whatever ruler2 was plus this string literal plus ruler2 again. So ruler3 is going to be 1 space 2 space 1 space 3 space 1 space 2 space 1. Right? So all these guys are spaces. So it's basically this guy jammed with this again to give you that, right? And then we do this once more to define ruler 4. So that's simply going to be 1, 2, 1, 3 1 2 1 4 1 2 1 3 1 2 1. All right, and all these guys are spaces. Okay, so we define these variables ruler 1 through ruler 4, and then we simply write the values of the 4 variables. We do a write ln of ruler 1, which is going to write this one along with a new line at the end. Then we write this one with a new line at the end, then this one, and then that one. Okay, so that's what the program does. So let's look at the output. We run the program by saying python3 ruler.py, and the program simply prints the values of each of those 4 variables, ruler 1 through ruler 4. Okay, so this is a very simple program that shows how you work with strings, how you define them, how you put strings together using the plus operator, and so on. All right. Now, for those of you that are somewhat mathematically minded, what this output is that it is related to what is called the ruler function. All right. So the ruler function, denoted r of n, is the exponent of the largest power of 2, which divides to n. All right. So what is, for example, r 5? Well, in this case, we are looking at the largest, the exponent of the largest power of 2 that divides 2 times 5, which is 10. So what's the exponent of the largest power of 2 that divides 10? Well, it's 3, because 2 to the 3 is 8. Sorry, it's 1, because 2 to the power 1 is 2, and 2 evenly divides 10. All right. No other power of 2 divides 10. The only power of 2 that divides 10 is 2, whose exponent is 1. So this guy is simply 1. All right. What about r of 4? Well, this is going to be 3, because r of 4 is the exponent of the largest power of 2, which divides 8. But what is the exponent of the largest power of 2 that divides 8? Well, it's 3. Because 2 to the 3 is 8, and that evenly divides 8. Okay, so that's the ruler function. And then what you see in the output here is that the ith row in the output lists the values for r of n. All right, where n goes from 1, 2, and so on, all the way up to 2 to the I minus 1. Okay, so for example, if you take this row here, so this stands for I equals 2. Okay, so what we do here, so this row is basically listing the values for r of n, where n is 1, 2, and 3. Okay, similarly, this row here is I equals 4, and it's what you see for these values are the values of the ruler function for n equals 1, 2, and so on, all the way up to 2 to the 4 minus 1, which is 15. Okay. All right. Okay, so a few more things about strings. Now, the built-in function stir can be used to convert numbers to strings. So there is in Python a built-in function called stir that you can call to turn a number into a string. We'll talk about what built-in functions are later. For now, just think of these as library functions. All right. And you can use this function stir in particular to convert a number into a string. Here are some examples. So you can take the integer literal 123 and turn it into the string 123 by using the stir function. So you can say stir of the integer literal 123 to give you a stir object whose value is the string 123. And similarly, you can take a floating point number 123.45 and turn it into the string object 123.45, again using the stir function. Okay, so the stir function comes in very handy when you're producing output. You can turn any type into a string, right? Likewise, the built-in functions int and float can be used to convert strings to numbers. So with stir, you went from a number to a string, but if you want to turn a string to a number, you could use int or float. For example, calling the built-in function int on the string literal 123 gives you the integer literal 123. Similarly, calling the float built-in function on the string literal 123.45 gives you the float literal 123.45. All right, so you can use a stir to convert numeric types to strings, and you can use the built-in functions int and float to go the other way around, meaning convert strings to numbers. Okay, now let's talk about the second built-in type in Python, which is quite fundamental, which is integer. So the integer data type denoted using the int keyword represents integers or rational or natural numbers in Python. Now we can specify an integer literal simply as a sequence of digits 0 through 9. All right, that's how you specify an integer literal. For example, the number 42. Right? That's an integer literal. So 42 is an example of an integer literal. Another example is 1234, and so on and so on and so on. Now, what are the operations that are allowed on integers? Well, you can perform all the arithmetic operations, which includes addition, subtraction, multiplication, integer division or floor division, remainder, and exponentiation. Right? So these are all the things that you can do on integers. So by floor division, we mean integer division. So for example, 12//5 is going to give you 2. All right. And if you want a floating point division, then you need to use single slash. But we'll talk about that when we get to floating point numbers. But if you want integer division, you put 2 slashes. Right. So that's what we call floor division. And percent is the remainder. So for example, 11% 5 is 1, because 1 is the remainder of 11 and 5. So here is then the summary of the integer data type. The allowed values are all integers, and typical integer literals are 1234, 99, 0, million, and so on. And then the operations that you can perform are the sign operation, meaning you can turn a number such as 42 into its negative by saying minus of 42. And doing plus of a number, x gives you x back, right? So plus as a unary operation simply has no effect. So those are the unary plus and minus operations. And then in addition, you can add two integers, you can subtract them, multiply them, perform integer division, you can calculate the remainder, and exponentiation, and these are the corresponding symbols, right? So you have the sign operators, plus, minus, and then you have addition, subtraction, multiplication, floor division or integer division, remainder, and exponentiation, all right? So now let's look at a concrete program called intops.py that shows you how you work with integers. So this program is fairly straightforward. What it does is it takes two integers a and b as command line arguments, and then it performs integer operations on those two integers and simply writes the results to standard output or the terminal. Okay. So let's walk through the program. The first thing that we do is import the modules of interest. So we import stdio because we are going to be using the write-ln functionality from there. And then we import sys because we are going to accept two integers as command line arguments. All right. So that's why we import those two modules. And then what we do is we define two variables, A and B, right, that store the two command line arguments that are given to the program, right? But here we do something very interesting. We receive the first command line argument, which is familiar syntax to us, okay? But remember that the command line arguments, they're stored as strings inside of sys.argv. But in the program, we want to treat each of the two command line arguments as integers. So we need to first convert the string into an integer. So this is where we make use of the built-in function int. All right. So int takes a string as an argument and converts it into an integer, which is what is assigned to A. So A is now the command line, the first command line argument, but as an integer, right? Because we use this conversion function. And the same thing for B. B is the second command line argument turned into an integer, right? So both A and B are now of type integer. The next thing that we do is all the arithmetic operations on the two integers A and B. So total is defined as a variable whose value is set to A plus B. Diff is another variable whose value is the difference of A and B, right? Prod is a variable whose value is A times B. Quotient is a variable whose value is the integer division of A and B. Remainder has the value which is the remainder of A and B, and X has the value which is A to the power B, right? So we're just defining these variables with these values. And then the last bit is to produce some output, right? So here we are saying A plus B equals the total, right? So we are simply writing the value of this variable total, but we're producing the output in sort of in a very readable way. So for example, if A was, let's say, 10 and B was 20, then total is going to be 30, and this output is going to be written out as the string 10 plus 20 equals 30. All right, so 10 is the value of this guy, 20 is the value of this guy here, and 30 is the value of this guy here. All right. Okay. Now, why are we calling this stir built-in function here? Well, A, B, and total, they are all integers. All right. But for the purpose of generating this output as a string, we need to make them into strings so that we can concatenate them with these string literals. So these guys are all strings. So if we want to concatenate these integer values to those strings, we have to first turn them into strings, which is why we are calling stir on A, B, and total. All right. So it's an error in Python to do something like 10 plus some string literal such as plus. So this is an error in Python unless you turn 10 into a string, in which case the whole thing becomes the string 10 plus. All right. So keep this in mind. Whenever you're concatenating a type that is not a string to a string, what you're concatenating needs to be first turned into a string. All right. But here I should also mention that if you're just writing one thing to the output without concatenation, then you don't have to invoke the stir function. So for example, let's say you just want to write A, the value of A to the terminal. So in that case, you can simply say stdio dot write ln of A. So since you're not concatenating A to any string, it's perfectly okay to write it out, though it was just it was an integer. Of course, I mean this you can also write this as saying stdio dot write ln stir of A. That's fine too. But the thing is, if you're just writing a out, you don't have to turn it into a string, right? You need to turn something into a string only when you're concatenating that with something else, such as what's shown here or what's shown here. Okay. All right. So what we're doing here then is simply writing out the values of all these variables, but in a nice readable manner, right? A user-friendly way. So in the first line, we say a plus b equals its value, a minus b equals its value, a times b equals its value, and so on and so on and so on. Okay, so we are simply writing each one of these guys out. Okay, so that's a very nice program that shows how you work with integers. All right. Okay. And here is the output. So we run int ops.py by saying python3 int ops.py, and then we specify the two command line arguments that the program expects. So in this case, the first command line argument is a, the second command line argument is b, right? So when you specify it here as such, they're strings, but then inside of the program we convert them into integers. So a is the number 1234 and b is the number 5, right? And then we go about calculating these guys for those values, and then we print out the results. So, so a plus b comes out as that, a minus b comes out as that, and so on and so on and so on, right? Okay, so the next data type that we're going to talk about is the third fundamental built-in type in Python, which is float. So the float data type, denoted by the keyword float, represents floating point numbers or real numbers in Python. And these are typically used for scientific and commercial applications. Now, the way you specify a floating point literal in Python is using a sequence of digits and with a decimal point. Okay. So for example, this literal 3.14159 is a float literal, and it's an approximation to pi. So that's how you would express a floating point number in Python, right? Now you can alternatively use this a notation that is similar to scientific notation, all right? So for example, if you want to represent Avogadro's number, which is 6.022 times 10 to the power 23, then you can simply write it using this notation, 6.022 e for exponent 23, right? So that has so that's basically how you represent this number here. So so this notation gives you an alternate way of expressing a real number in Python, right? And it comes in very handy when you're representing very large or very small numbers. So keep that in mind. Now, what are the operations that you can perform on real numbers or floating point numbers? Well, here again, you can perform arithmetic operations. So given floating point numbers, you can add them, you can subtract them, you can multiply them, you can divide them. So slash here means floating point division, and then you can also exponentiate. Okay, so those are the operations that you can perform. So here then is the summary of the float data type. The values are all real numbers. Typical literals look like these: 3.14159, which is an approximation to pi, 6.022 e to the 23, that's sort of like scientific notation, representing Avogadro's number, 2.0, and then 1.14 blah blah blah, and so on and so on. Okay, so these are some typical float literals. What are the operations that you can perform? Here again, you can perform the unary sign operation, plus or minus, and then you can add two floating point numbers. You can subtract them, multiply them, divide them, and exponentiate them. And then these guys are the symbols, the corresponding symbols. The unary plus and minus, addition, subtraction, multiplication, floating point division, and exponentiation. All right. So now let's look at a program called floatops.py, that illustrates how you work with floating point numbers and how you perform operations on them and so on. So this program, similar to int ops.py that we saw before, what it does is it accepts two floating point numbers, a and b, as command line arguments, and it performs floating point operations on those numbers and simply and then writes the results to standard output or the terminal. Okay. So this program is going to be very similar to int ops.py that we saw before, except that here we work with floating point numbers. Okay, so here again we import stdio and sys. Stdio because we are using the write functionality from there, and sys because we needed to process command line arguments. And then we receive the two command line arguments as strings and then turn them into floats using the float built-in function. Okay, so in the previous program we used int to turn strings to ints. Here we use float to turn the command line arguments, which are strings, into floating point numbers. Okay, and once we have the two floats a and b, we perform floating point operations on them. So total is the sum of a and b, diff is the difference of a and b, prod is the product, quotient is the quotient, and exp is a to the power b. And then finally, we simply write the values of those variables out using an idea similar to what we did in int ops.py. So here again, notice that a, b, and total are floats. Since we are concatenating those values with some strings, such as these guys, we first need to turn the floats into strings. And we achieve that using the stir built-in function. All right. Okay, so here we are simply constructing some nice output string and then printing it out using the writeln function. So we do that for each of these variables here. All right, so let's look at some output. So if we run floatops.py with the command line arguments a equals 123.456 and b equals 78.9, the program comes back with this output. Okay. So this line of output is from here, this line of output is from here, and so on, and finally this line of output is from that function call. All right. Okay. Let's now look at a slightly more interesting program where we work with floating point numbers. So this program is called quadratic.py, and what it does is it takes two command line arguments b and c as floating point numbers, and then it computes the roots of the quadratic equation x squared plus bx plus c equals 0. Okay, and notice that it's not quite in the standard form ax squared plus bx plus c equals 0 because we have set a to be 1 always. All right, so here the quadratic equation is x squared plus bx plus c equals 0. Now we know that the roots of the quadratic equation ax squared plus bx plus c, so if you have ax squared plus bx plus c, then we know that the roots of this equation are simply x equals minus b plus minus square root of b squared minus 4ac divided by 2a. That's the formula. But then in our case, we are setting a to be 1. So the formula is basically minus b plus or minus b squared minus 4c divided by 2 because a is set to 1. And that's what we have here. So what the program does is it takes b and c as inputs and simply prints out the values of the square roots of this quadratic equation, which are given by this formula here. Okay, and those square roots are roots are then written to the terminal or standard output. Okay, so let's go through the program. So here we first import math. And we need math because we're going to use the square root function from there, right? So we need to import the math library. Just telling Python that we're going to use that square root functionality later on from the math library. And then we import the usual stdio and sys modules, right? We first read the two command line arguments, b and c, as floating point numbers. So here again, notice that we turn the string command line argument into a float. All right. So B and C are floating point numbers representing these guys in the quadratic equation. And then we define a variable called discriminant to store this part of the formula. So the stuff inside the radical or the square root is what we call the discriminant. So we calculate that separately as b squared minus 4c and simply store it in a variable, right, called discriminant. And then what we do is, the next thing that we need to do is calculate the square root of the discriminant, which is what we do here. But to do that, we make a call to the square root function from the math library that we have imported here. So we say math.square root and we give discriminant as an argument, and then that comes back with the square root, which we assign to this variable little d, right? And then all that we need to do is calculate the two square roots as minus b plus square root of b, the discriminant divided by 2, and minus b minus the square root of discriminant divided by 2. Okay, so this part here is minus b square root of d, the discriminant divided by 2, and then this part here is plus, and then this part here is minus b minus the square root of discriminant divided by 2. That's the other. So this is root 1 and this is root 2. All right. So we simply calculate the two square roots and print them out. Notice that you could have also saved this into an intermediate variable and called it like root 1 and printed out root 1 if you want, but you don't have to do it. Similarly, you can assign this expression to another variable called root 2 and then write that out. All right. Okay, so that's that. Now let's look at some output. So we run quadratic.py first with the arguments minus 3.0 for b and 2.0 for c. And the program comes back with two roots, 2 and 1. So in this case, what is the quadratic equation that we are referring to? It's x squared minus 3x plus 2 equals 0. And these are the two roots of that equation, right? And then the next time around, we are running it with minus 1 for b and minus 1 for c. In this case, we are talking about that quadratic equation x squared minus x minus 1 equals 0. Okay? And then in the last instance, we are running it with b equals 1 and c equals 1, in which case we are talking about the quadratic equation x squared plus x plus 1 equals 0. Now in this case, the program comes back with an error. Why is this? Well, what happens here is, since b is 1 and c is 1, when we get to calculating the discriminant, what do we get here? Well, it's 1 times 1 minus 4 times 1, and this gives us minus 3. And then here we go about calculating the square root of minus 3, the square root of a negative number, and that fails, and that's the error that you see here, all right, because you're asking for the square root of a negative number. So this implementation of the quadratic program is not quite set up to handle complex roots, right? Because it can only deal with roots that are real numbers, all right? Okay. So this is an example of a program that makes use of real numbers to solve a very interesting problem, namely figuring out the roots of a quadratic equation, all right? Okay, so the last type that we're going to discuss in this section is the fourth fundamental type, built-in type in Python, namely the Boolean data type. So the Boolean data type, denoted by the keyword bool, represents the truth values true or false from logic. Okay, so this data type just has two possible values, true or false. Now in Python, the Boolean literals are represented as true and false, but they're with a capital T and a capital F, right? So if you want to talk about true, write it as true with a capital T. If you want to talk about false, write it as false with a capital F. So these are the two Boolean literals and the only Boolean literals, all right? Now, what are the operations that you can perform on Boolean values? Well, you can perform the logical AND, the logical OR, and logical NOT. Okay, to understand how these operations work, we need to understand how their truth tables work. And we already know about these truth tables from our lecture on building a computer. All right, so here is the truth table for logical AND. So AND is a binary operation. It has two inputs. So there are four possible values here for the inputs. And the output is a 1 or a true precisely when both inputs are true. So that's how logical AND works. Here is the truth table for logical OR. OR is also a binary operation. So it has two inputs, X and Y, and four possible values for the inputs. And the output is a false exactly when both inputs are false, and in all other cases the output is true. And then finally here you have the truth table for the logical NOT, which is a unary operation, so it just has one input, so just two possible values for the inputs, true and false, and the output is simply the opposite of the input. So when the input is false, output is true. When the input is true, the output is false, right? And finally, here is a summary of the Boolean data type. The values are simply true and false, denoted by these literals. True with a capital T for true, false with a capital F for false. These are the operations that are allowed, and OR and NOT, and these are how they are represented in code. All right. So that's logical AND, logical OR, and logical NOT. Okay. Now, let's talk about what are called comparison operators. So the comparison operators are all these guys: equals, equals, not equals, less than or equal to, greater than or equal to, is and is not. And these are defined for both integers and floats, and they evaluate to produce a Boolean result. Okay, so what that means is you put an operator here, a comparison operator, which is one of these guys, and on either side you can have a numeric type, right, such as an integer, so integer or float, and on this side you can have an integer or float, and here you can put any one of these guys, so equals, equals, not equals, and so on and so on and so on. Less than, greater than, less than or equal to, greater than or equal to, is not. Okay, so those are the things that can go in here in the box, and on either side you have a numeric type. Now the whole thing, this is interesting, so the whole thing is an expression whose type is Boolean, meaning it has a value that is true or false. All right, so here are some examples. So you can say 2 equals 2 to check if 2 is equal to 2, and of course that is going to evaluate to true, because this whole thing is a Boolean expression whose value is true. Here we are checking if 2 is equal to 3 or not using the equals comparison operator. So this whole thing is a Boolean expression whose value is of course false, because 2 is not equal to 3. And then in here we compare 2 with 13 using the less than operator, and this evaluates to a Boolean expression that is true, because 2 is actually less than 13, right? So that's how comparison operators work. They operate on numeric types, but the end result is a Boolean expression with the value true or false. Now in terms of precedence, comparison operators have lower precedence than arithmetic operations, meaning arithmetic is done before comparison, but comparison operators have higher precedence than Boolean operations, meaning comparison operations are performed before Boolean operators. Okay. Now, if you have an expression like this with parentheses, it turns out that you can completely drop the parentheses and entirely rely on the precedence rules, and that would do what you wanted to do with the parentheses, right? Because, for example, here, what sort of operations do we have? We have arithmetic operations and the comparison operator, but arithmetic comes before comparison, which is what we are saying here. So all this stuff is going to be evaluated first and then compared with 0 using this comparison operator. So here we really don't need the parentheses, and we can entirely rely on the precedence rules. But it's often a good idea to put parentheses just for clarity. So it makes it very clear that you want this thing to happen before the comparison. All right? Okay, now let's look at a program where we make use of Boolean variables. So this program is called leapyear.py, and it accepts a single command line argument as an integer, and we're going to call this argument year. And what it's going to do for output is it's going to write true or false. True if that year is a leap year, and false if it is not a leap year. All right? And the logic for testing if a year is leap year or not is as follows. So we say a year is a leap year if it is divisible by 4 and it is not divisible by 100, or it is divisible by 400. Okay, so we use a combination of these logical operations to figure out if a year is a leap year or not. So again, a year is a leap year if it is divisible by 4 and it is not divisible by 100, or it is divisible by 400. So not every century is a leap year unless it is divisible by 400. All right. Okay. So here is the code that implements this idea. So we import the two modules stdio and sys. Stdio because we need to write some output, sys because we need to process command line arguments. So this program takes one command line argument, and we treat it as an integer inside of the program because it's going to represent a year, and it's this year that we want to test whether it is leap or not. All right. So we create a variable, we define a variable called is leap year and set it to the remainder of set it to how the remainder compares to 0. So I hope you guys see that this value here, year remainder 4, is simply what you get as a remainder for year and 4. Okay, so that's an integer clearly, and then 0 is an integer. So we are comparing two integers using the comparison operator equals. So this whole thing is a Boolean expression. All right. So what we are saying here is year evenly divisible by 4? Does 4 evenly divide year? If so, is leap year is true, otherwise it is false. All right. Okay. And then we say the new value for is leap year is the logical AND of these two Boolean expressions. All right. So we are saying it is the logical AND of whatever the value of is leap year was from here, and year not divisible by 100. Okay, so notice that here we are comparing the remainder of year and 100 with 0 using the not equals operator. So in other words, what we are saying here is his leap year is the current value of his leap year, logical AND year not divisible by 100. Okay, so we are basically implementing this idea, divisible by 4 and not divisible by 100. All right. And then finally, we implement this part. We say that the new value of his leap year is the current value of his leap year or year divisible by a 400. Okay, that's this part. So what we have said in these 3 lines is that a year is a leap year if it is divisible by 4 and it is not divisible by 100, or it is divisible by 400. Okay. If after all these checks, if is leap year is true, If this value is true, then year is a leap year. If this value is false, then year is not a leap year. So what are we doing here? We're simply printing the value of the variable is leap year, and that's going to be true or false. True meaning year is leap, and false meaning year is not a leap year. All right. So let's look at some output. So we first run the program, giving it the command line argument 2016. So year is now 2016 as an integer. So we first check if year is divisible by 4. Well, this number is clearly divisible by 4, so is leap year is going to be true. Okay, and then we check if this guy is true and if this guy is true, right? Well, is leap year was true, and 2016 is not divisible by 100, so this is also true, so is leap year continues to remain true. And then finally we check here if this guy is true, which it is, or year is not divisible, year is divisible by 400. Well, year is not divisible by 400 because year is 2016, so this part is false, but that's okay. What we have here is a true or false, which is true. So you just have to go back to the truth table for or. So is leap year is true, and that's what we print. Now, in many programming tasks, you cannot simply rely on built-in operations to get your job done. All right, so you have to go beyond the built-in operators such as arithmetic operators and logical operations and so on, and you need to make use of functions, right? Because there is only so much that you can do with built-in operations. Now, in this course, we are going to consider 3 kinds of functions. We'll first consider what are called built-in functions, and we have already seen examples of these: int, float, and stir. And these are functions that you can use directly inside of your Python program. You don't have to import them, right? So the built-in functions come to are given to you for free. You don't have to import any module in order to be able to use these functions. And then we're going to make use of standard functions such as square root from math, which is what we did in the quadratic program. And these are defined inside of modules. So you have to import the corresponding modules, right? So for example, if you want to make use of square root, you need to import math. Okay. And then finally, we'll make use of user-defined functions such as the write function from stdio and write-ln. And these are defined in third-party modules. Okay, so stdio is not given to us by Python, but it's defined by the authors of our text, right? Whereas math is a module that is given to us by Python. It's a standard module. Okay, whereas stdio is a third-party module. Okay, so to summarize, we're going to use 3 types of functions. And we need functions to implement most programming tasks. So we're going to use 3 types of functions: built-in functions that come for free, such as int, float, and stir. You don't have to import anything for these. And then we'll make use of standard functions sitting inside of standard modules. These are given to us by Python. And to use these functions, you have to import the corresponding module, for example, math, to be able to use the square root function from there. And then we'll also make use of user-defined functions defined in in third-party modules. Okay, so these are not from given to us by Python. And here again, we have to import the corresponding modules. So if you were to use write and write-ln, you have to import the stdio module. Now, the way you call a function in your code is by typing the name of the function followed by the arguments to the function, which are simply expressions, and these arguments are enclosed in parentheses and separated by commas. And we've already seen examples of this. So for example, if you want to call the square root function, you simply say math.square root, because square root belongs to math, and then you specify in parentheses any arguments to that function, which are simply expressions. All right. So in this case, there was just one argument, the number for which you want to calculate the square root. So the syntax again is very simple. It's the name of the function followed by the arguments specified in parentheses separated by commas. Now, when Python executes a program, we say that it calls or evaluates the function. So when it executes this piece of code, we say that Python calls this function sqrt from the math module to compute the square root of this number. All right. Now, a function called may or may not return a value, but the one that returns a value is basically an expression. So you can use a call to such a function in the same way you use variables and literals to build more complicated expressions, right? So let me give you an example of that. So here we are making calls to the function sine and cosine from the math library with some arguments x and y. Okay, and these functions return a value. So sine returns the sine of x expressed in radians, and cosine returns the cosine of y expressed in radians. So since they return values, you can use them just like expression. So this guy has a value with some type, which in this case is float. This guy has a value which is also of type float, and then you multiply the two using an allowed operation, in this case the arithmetic operation multiplication, and you build a more complex expression whose type is now a float. Okay, so that's what we're saying here. A function that returns a value can be treated as an expression. All right. What about a function that doesn't return a value? Well, in that case, you cannot treat it as an expression, but you use it only for its side effect. All right, and you use it basically as a statement. And here is an example of that. So stdio.writeln is a function that doesn't return a value, but it surely has a side effect, which is to print this message to the terminal. Okay, so you would never use stdio.writeln as an expression, but you would always use it as a statement, meaning a line of code in itself. All right. And you're basically using it only for its side effect, which in this case is to write this message to the terminal, and writeln doesn't return any value. All right. Okay, now we typically summarize functions in a table called the Application Programming Interface, or API for short. So API is essentially a way of documenting the functions inside of a library. So here is the API for the built-in functions in Python. So remember that these are functions that you can use directly without importing, right? So here are some examples. So ABS, what it does is it takes a number as an argument and returns the absolute value of it. So ABS of minus 42 is simply 42, right? And then max takes two numbers and returns the maximum of the two. In fact, it can take any number of numbers. So max of 2 and 7 returns 7, all right? Okay, and this table is what we call the API for the built-in functions. And what this table contains is essentially two columns. The first column lists the names of the functions in that library, along with the corresponding arguments. And the second column gives you a short description of what each function does, right? So that way, just by looking at this table, you know exactly what functions are supported by the API and what they do. Okay. Here is the API for the standard functions from Python's math and random modules. So math has a whole bunch of functions that you can that are related to doing mathematics. All right. So here, for example, sine takes some angle in radians and returns the sine of that angle. Cosine returns the cosine of an angle expressed in radians. And there are many other methods inside of many other functions inside of math. Okay. So this is the API for the math library. Here is the API for the random library from Python, right? So random is a function that doesn't take any argument and returns a random number, a random float from the interval 0 through 1, right? Where 0 is inclusive and 1 is not inclusive, right? So it's simply a number between 0 and 1. Picked at random. And then rand range is a function that takes two arguments as integers x and y and returns a random integer from the interval x through y, where x is inclusive and y is not. So for example, if you want to use the function randrange to simulate a coin flip, you would say something like random dot randrange one, or we could say 0 and 2, right? So x is 0 and y is 2. So randrange, the only possible values that it will return are 0 or 1 picked at random. All right. Why is it not going to return 2? Well, look at the documentation. The second argument is not inclusive. All right. So this will return 0 or 1 with probability half, right? So if you make 100 calls to this function with these arguments, you'll get 0 about 50% of the time, and you'll get 1 about 50% of the time, right? Another example is if you were to use this function to simulate the roll of a six-sided die, you would say something like random dot randrange 1 through 7, because the right bound is not inclusive. So this call is going to return a random number between 1 and 6, right? And that simulates the roll of a six-sided die. Here is the API for the Stdio module that we have been using for producing output. Okay. Now this is Stdio is a user-defined module, right? And here is its API. So the write function takes a message x and simply writes it out without a new line at the end. And then write ln takes a message x and writes it with a new line character at the end. Now we can use the built-in functions int, float, stir, and round to explicitly convert from strings to integers or floats, and vice versa. And we've already seen these three guys. And round is also a function that you can use to for conversion, for type conversion. Okay. And Python also supports implicit conversion, which is also called automatic promotion or coercion. For example, we can use an integer where a float is expected, as in mat.square root of 4. So square root really expects a floating point number, but you can give it an integer. But Python will automatically promote that argument 4, which is an integer, to 4.0, and then calculate its square root as 2.0. Okay, so there is some implicit conversion that is going on here, which is what we call promotion or coercion, right? So this 4 is turned from an integer into a floating point number. Okay, so the last bit in this lecture is to talk about using Python as a calculator, and you can do that by running the command python3 on the terminal without any input. So on the terminal, simply say python3, and when you do that and hit enter, you will be put into what we call the Python shell environment, and that is denoted by these 3 greater than sign. So inside of the Python shell, this is the prompt, all right, 3 greater than sign. And in that environment, in that Python shell, you can use Python as a very simple interactive calculator. So for example, at that prompt, you can type 1 plus 2 and you get the result 3. You can even define variables. So you can set a to 1, for example, and b to 2. And then when you say a plus b, it comes back with the result 3. You can import a module using the standard import syntax, and then you can go about using the functions from that module. So for example, you can calculate the square root of the number 2 by saying mat.square root of 2, and you get the result back. Okay, so as you can see, you can use the Python shell very effectively as a simple calculator, and I would highly encourage you guys to use this feature of Python. Okay, so you can test out your ideas in this environment before you actually put it in code inside of a Python program. All right. And then you can also access some constants from the math module by simply saying math.e, in which case you get the Euler's constant. You can also say math.pi to get pi and so on. In addition, inside of the Python shell, you can write call the dir function by saying dir in parentheses, and that simply prints things that are defined in the current environment. So for example, it's saying that A was defined, B was defined, math is defined, and so on. That's because we defined A and B explicitly and we imported math. Okay. Now, what's more important is you can say dir and specify a library name as an argument. Okay, so if you say dir of math, where math is a module, what dir does is it simply prints everything that is supported by math. So it's basically listing all the functions that are available inside of the math library. For example, sine, square root, log, tan, and so on and so on and so on. So you can very nicely use the dir function to get a sense of what is supported by a library. You very easily list the functions that are supported by a library using the dir function, right? In addition, you can also use the help function. So you can say help and the name of a module such as math to get detailed documentation on that library. So here what you're seeing is basically the API for math. Okay, so it tells you the name of the module, it gives you a short description of what the module is, and then it lists all the functions that are available inside of the module along with a short description for each of the functions. So here is the description for arc cosine. Okay, and then it also lists the constants that are available. So with math, there are two constants available, e and pi, Euler's constant and pi. Right, so this is a really fantastic feature in Python. You can get detailed documentation on any module by running the help command on that module, right? And essentially what you're getting is the like offline access to the API for a module, right? So you're basically getting offline help for everything that Python supports. So I would strongly encourage you guys to make good use of this feature of Python, which is that you can run Python interactively on the terminal and do interesting things. You can do computations and you can also check the documentation, right? And finally, the way you get out of the interactive Python shell is by running the exit command, right? So if you just say exit as a function call, meaning exit parenthesis and hit enter, you come back to the prompt of the terminal. Okay, so that's how you get out of Python shell. Okay, so with that, we conclude this lecture on the built-in data types in Python. Thanks for your time.